Welcome to the deep dive. This is where we, really get into the details, cutting through the noise to find the core insights from complex research.
And today, we've got quite a task ahead of us. We're diving deep into Universe, Life, Reason by Yusuf Shklovsky. Foundational stuff.
Absolutely. And our mission today, for you listening, is pretty specific, but honestly, fundamental to understanding, well, everything out there.
That's right. We're aiming to build a really solid, structured understanding of how we characterize stars, the basics.
And we'll see how they're classified, mapped out on the Hertzsprung-Russell diagram.
And then, this is the crucial bit, connect all those stellar properties directly back to why life, biological life like us, can even exist, the chemistry.
Okay, let's kick things off with something Shklovsky points out early on that feels, well, kind of backward, almost paradoxical.
Ah, yes. The idea that astronomers, even back then, felt they understood how stars form and evolve.
Often better than how our own solar system, our planets, came to be.
It sounds weird, doesn't it? But think about it from an observational standpoint.
It's about the sample size, right?
Exactly. When we look out into the galaxy, we see, countless stars. Billions upon billions.
And crucially, we see them at every single stage of their life cycle.
Precisely. From the clouds where they're born, the stellar nurseries, all the way to, well, their end states. White dwarfs, neutron stars.
So we get this huge library of examples, like seeing baby pictures, teenage angst, midlife crisis, and retirement snapshots all at once, but for stars.
That's a great way to put it. It lets us build and test theories about the whole process, but looking at other planetary systems in detail, especially how they form.
That's incredibly hard even today. Getting the chemistry, seeing the early stages.
It's a huge challenge. So, yeah, we have this fairly complete picture for stars. Even the specifics of our own planetary backyard are still, a bit fuzzy in places.
That really sets the scene. So to build that complete stellar story, we need to get a grip on the four fundamental ways astronomers measure and classify stars.
4 pillars, as you called them earlier: mass, luminosity, radius, and surface temperature. Get these, and you can start to understand any star.
Right. Let's start with mass. It feels like the most fundamental thing, doesn't it? It controls everything the star's life, its power.
It absolutely does. But here's the kicker Shklovsky emphasizes. While it's critical, the actual range of star masses isn't as vast as you might think. It's comparatively narrow.
We measure it against our sun, right? Solar mass, which is, what, about $2 tons, 10 grams?
Yep. Roughly 330,000 times the mass of Earth. Massive from our perspective, but in the grand scheme of stars.
It's sort of mid-range.
Yeah.
Because the source says very few stars are more than, say, 10 times the sun's mass or less than about a tenth of it.
Exactly. There are physical limits. Too small, and you don't get fusion. You get a brown dwarf, a failed star.
And too big, like 100 times the sun.
They become incredibly unstable. They burn through their fuel so violently, so quickly, they just don't last long and might even tear themselves apart. Fusion physics kind of sets these boundaries.
So mass sets the potential. But the next killer, luminosity L, is the actual power output, and that varies wildly.
Oh, hugely. Luminosity is the total energy pouring out of the star every second. Our sun pumps out about $4.10 ergs per second.
Which sounds like a lot.
It is, but compare it to other stars, unlike mass, where we saw maybe a factor of 100 or so between the common extremes.
Luminosity differences can be hundreds of thousands, even millions.
Right. You have these supergent stars, relatively rare, but they can outshine the sun by tens, even hundreds of thousands of times. Absolute cosmic lighthouses.
But they're the exception, aren't they? The source says the vast majority are dwarfs.
Correct. Most stars are much, much fainter than our sun. Thousands of times less luminous, often. So our sun, in terms of pure energy output, is actually pretty bright compared to the galactic average.
Okay, that leads us neatly into radius and this density paradox you mentioned. Because if the mass range is narrow, but the physical size of the radius can be vastly different.
Then the densities have to go to extremes. This is where you really start to see the different types of stars emerge.
So radii can go from tiny, like Earth-sized white dwarfs
all the way up to red giants, these enormous, bloated stars that could easily swallow the inner planets out past Mars, even.
Let's try and picture those densities.
Yeah.
Our sun's average density is about 1.4 grams per cubic centimeter, a bit denser than water.
Pretty ordinary stuff, density-wise. Now, take that red giant bubble, same sort of mass as the sun, maybe a bit more, but inflated to this incredible size.
The density must plummet.
Absolutely. Shklovsky notes it's millions of times less dense than the air we breathe. It's practically a hot vacuum, just incredibly spread out plasma.
Okay, flip side. The white dwarfs. Small radius, maybe Earth-size, but still packing a fair bit of leftover mass, right?
Exactly. All that mass crammed into such a tiny volume, the density goes through the roof.
How dense are we talking?
Tens of thousands, maybe hundreds of thousands of grams per cubic centimeter. The classic example is, a teaspoonful would weigh tons. It's matter pushed almost to its breaking point.
Wow. Okay, fourth pillar. Surface temperature. This seems more intuitive because it's what gives stars their color.
It's the most immediate visual clue, definitely. And it dictates the kind of light we get, which is key for figuring out everything else.
So the cooler ones, 3,000 to 4,000 Kelvin.
Yeah.
They look reddish.
Yep. Then you get up to stars like our sun, around the 6,000 K, nice and yellowish.
And the really hot ones, over 10,000, 12,000 K.
Those are blazing white, even bluish, really intense. And this temperature-color link is exactly what we need to move on to the next step, figuring out what stars are made of using their light. Spectroscopy.
Right.
Spectroscopy. This is where things get really clever. It's like stellar forensics. You take the star's light, spread it out into a rainbow spectrum.
And read the barcodes, basically, the dark lines.
Exactly. Those absorption lines and sometimes emission lines are like a unique fingerprint. They tell you the temperature with incredible precision, but also the pressure in the star's atmosphere, and crucially for our story today, the chemical composition. It's the go-to tool.
And one objective way to measure that color, linked to temperature, is the color index. That comes from older photographic methods, doesn't it?
It does, yeah. It's a bit historical, but still useful. It compares how bright a star looks on an old blue-sensitive photographic plate versus how bright it looks visually, which is more sensitive to yellow-green light.
So a hot blue star would look brighter on the blue plate.
Meaning it gets a smaller magnitude number on that scale. Remember, magnitude is inverse, smaller means brighter.
Right, smaller magnitude on the photographic plate than the visual one.
Huh.
So the difference, photographic minus visual, is negative.
Precisely. Hot blue stars have a negative color index. Cool red stars, on the other hand, put out much more red and yellow light than blue.
So their visual magnitude is brighter, smaller number, than their photographic magnitude, giving a positive difference.
A large positive index, yeah. The source mentions 1.5 magnitudes, or even more for really red stars. It gives astronomers a hard number for the color, linking directly to temperature.
And that color index, or just the spectrum itself, lets us slot stars into that famous sequence, OBA-FGKM.
The spectral classes. Every astronomy student learns the mnemonic, "Oh, be a fine girl, guy, kiss me," runs from hottest O to coolest M.
It's the fundamental organizing principle.
Absolutely. And it's not just broad categories. For more precision, each letter class is subdivided into 10 parts, 0 to 9.
So a G2 star, like our sun, is slightly hotter than a G5 star, which is hotter than a G9, which is almost a K0.
Exactly. It gives you a very fine temperature scale, and the details in the spectrum change dramatically along this sequence.
Okay, let's walk through that. Start at the cool end, M and K stars, reddish. What do their spectra look like?
Because they're relatively cool, molecules can actually survive in their atmospheres. So you see these broad, fuzzy absorption bands from simple molecules like titanium oxide, TiO, carbon monoxide, CO, sometimes even water vapor, plus lines from neutral metal atoms.
But as you heat things up, moving towards G and F stars, like the sun.
Those molecules get ripped apart by the heat, the molecular bands vanish, the neutral metal lines start to weaken because the atoms are getting ionized, losing electrons.
And you start seeing lines from the ionized atoms instead.
That's right. Our sun, a G2 star, is famous for having really strong lines of ionized calcium, for example, right near the violet UV part of its spectrum.
Okay, keep heating up. What are the really hot ones, O and B stars? Over 20,000 Kelvin.
It's just extreme. The energy is so high, almost everything is ionized. Helium, which is tough to ionize, starts showing strong lines, both neutral and ionized helium, and the overall light output is heavily skewed towards the ultraviolet.
But there's a sweet spot around 10,000 K, the A-type stars, where hydrogen lines are strongest. Why is that?
Yeah, it's a bit counterintuitive. Hotter stars have less prominent hydrogen lines because the hydrogen is mostly ionized. Cooler stars don't have enough energy to excite the hydrogen electrons efficiently. A stars hit that perfect temperature, around 10,000 K, where hydrogen is easily excited but not completely stripped, making its spectral lines incredibly strong.
So the spectral class gives us temperature and chemical clues. It's this classification, combined with luminosity, that lets us build the big map, the Hertzsprung-Russell diagram.
Exactly. The HR diagram, if spectroscopy is the fingerprint, the HR diagram is like the FBI's central database, organizing all the suspects. It plots stars based on their intrinsic properties and reveals fundamental patterns.
It was a huge breakthrough, wasn't it? Developed independently by Hertzsprung and Russell over a century ago, really.
Oh, absolutely. It turned stellar astronomy from just cataloging into a physical science. It showed relationships nobody expected.
So let's lay out the axes for everyone listening. The horizontal axis, the x-axis or abscissa. That's the spectral class, right? OBAFGKM.
Correct. Which, as we just established, is basically a proxy for surface temperature. Hottest on the left, coolest on the right.
And the vertical axis, the y-axis or ordinate, that's luminosity.
Well, yes, but specifically it's plotted as absolute magnitude. We need to be clear about this. It's not how bright a star looks from Earth, because distance messes that up.
Right. Absolute magnitude standardizes the distance. It's how bright a star would appear if you placed it exactly 10 parsecs away.
10 parsecs. That's about 32.6 light years. It's just a convention, but it lets us compare the true inherent power output of stars on an equal footing.
Give us that sun example again. It looks incredibly bright to us.
Apparent magnitude is negative 26.8, dazzling. But if you moved it out to 10 parsecs, which is about 2 million times farther away than it actually is,
Its brightness would plummet.
dramatically. Its absolute magnitude is about +5. You barely see it with the naked eye on a clear night. Most visible stars are intrinsically much brighter than the sun.
And we need to remember that magnitude scale is backward. Brighter stars have lower or even negative numbers.
Exactly. So really luminous stars might have absolute magnitudes of -5, active, or 7. Faint stars have large positive magnitudes like +10, +15, even +20.
So Hertzsprung and Russell plotted thousands of stars using spectral class temperature on the x-axis and absolute magnitude luminosity on the y-axis. And they didn't just get a random scatter of points.
Not at all. The stars fell into distinct regions, clear groupings. 3 main ones stand
The
out.
most prominent is that diagonal slash across the middle, the main sequence.
Yep, a relatively narrow band running from the top left, hot, bright, massive stars, down to the bottom right, cool, dim, low-mass stars.
And this is where most stars spend most of their lives.
The vast majority, yes. This is the hydrogen running phase. Our sun is a typical main sequence star right in the middle.
Okay, group 2, up in the top right corner.
Those are the red giants, and as the name
Wow.
implies, they are spectral classes, K and M, sometimes G, so they're cool on the surface.
But they're way up high on the luminosity axis. Absolute magnitudes maybe +2 down to Manning 6 or even brighter.
Right. Cool surface, but very luminous overall. The only way that works is if they are physically enormous, huge radius, bloated, dying stars.
In the third group, down in the lower left.
For white dwarfs, these are fascinating. They're hot spectral classes, B, A, F, usually so they belong on the left side of the diagram.
But they're way down low on the luminosity scale.
Yeah.
Absolute magnitudes fainter than +10 typically.
Exactly. Hot surface, but very low total light output. What does that tell you?
They must be incredibly small. Tiny radius.
Bingo! Confirms that density paradox perfectly. These are the super dense, cooling embers of stars that have finished their lives. Small, hot, but fading away. Now that HR diagram showing those 3 groups, it's incredibly useful, but it comes with a huge caveat. We have to talk about observational selection.
Ah, right. The idea that what we see easily isn't necessarily what's most common.
Exactly. That standard HR diagram, let's call it the catalog diagram, is heavily biased. Think about how astronomers build catalogs. They tend to find the bright stuff first.
And you can see bright things from much farther away.
Precisely. Those luminous red giants and the hot, bright O and B stars on the main sequence, we can spot them across vast distances, thousands of light years. So they seem really numerous in our surveys.
But the little guys, the faint red dwarfs down at the bottom right,
They are incredibly dim. You can only see them if they're very close by, relatively speaking, maybe within a few dozen or perhaps 100 light years for detailed study. So they are massively underrepresented in diagrams based on large-scale surveys.
So to get the true picture of what stars are actually most common in a typical chunk of space, Shklovsky says we need to look at our immediate neighborhood.
Yes, zoom right in. Consider a small sphere around the sun, say with a radius of 5 parsecs. That's about 16.3 light years. What stars do we find in there?
And the picture changes completely, doesn't it?
Dramatically. First striking finding in that local 5 parsec bubble, there are 0 giant stars, none. They're just too rare.
Wow. Okay, so what is in there?
It's overwhelmingly dominated by the stars at the bottom right of the main sequence. The faint, cool, low-mass red dwarfs. They are by far the most common type of star.
Which makes our sun look pretty special, actually.
It really does. Our sun's a G2 star. In that local volume of roughly 50 stars and brown dwarfs, only 3 stars are intrinsically brighter than the sun: Sirius, Altair, and Procyon. Everything else is fainter.
So the cosmic average isn't a sun-like star, it's a dim little red dwarf.
Statistically speaking, yes. Probably 75%, maybe more, of all stars in the galaxy are red dwarfs.
What about the white dwarfs? The dead stars, how common are they locally?
That's another key finding. In that small 5-parsec volume, we find 5 white dwarfs.
5 dead stars just in our immediate vicinity.
Yep. Which implies when you scale that density up to the entire galaxy that there must be billions of them out there, maybe 10 billion or more, slowly cooling off. A huge population of stellar remnants.
It's amazing how changing the sample reveals the underlying reality. What about other groups? The source mentions subdwarfs.
Yes, the subdwarfs. They tend to appear on the HR diagram slightly below the main sequence for their temperature.
Meaning they're less luminous than a normal main sequence star of the same color.
Exactly. And their distribution is interesting. They aren't very common right near the sun in the galactic disk where we are, but they seem to be much more concentrated towards the center of the galaxy, and especially in the galaxy's halo and in old globular clusters.
So they might actually be incredibly numerous overall, just not primarily in our local neighborhood.
Some astronomers think they might even be the most numerous type of star in the entire galaxy, particularly if you count those older populations.
And why are they less luminous? What makes them different? This ties back to chemistry, right?
It does, perfectly. Subdwarfs are defined by having a significantly lower abundance of heavy elements. Astronomers call it lower metallicity compared to stars like our sun.
And that lack of metals changes their internal physics.
Yes. Fewer heavy elements means the star's interior is less opaque, less resistant to energy flowing out. This changes the star's structure, usually making it slightly smaller and therefore less luminous for its temperature, placing it below the main sequence. It's a direct chemical signature affecting its place on the HR diagram.
Okay, so the HR diagram isn't just a snapshot. The moment astronomers saw those patterns, they knew it had to relate to how stars change over time. Stellar evolution.
Absolutely, it became clear it was mapping out life stages. Now, the first guess about the evolutionary path was, well, intuitive but wrong.
The naive theory, the source calls it, that stars started big and cool, then heated up and cooled down along the main sequence.
Exactly. The idea was start as a red giant, contract under gravity, heating up, become a hot blue giant, top left of HR, then evolve down the main sequence, cooling off from O, B, A, F, G, K to M.
It sounds sort of logical, like a cooling ember.
It does, but it had major problems. The biggest was that it required stars to somehow shed enormous amounts of mass as they cooled, which didn't really make sense physically.
And it completely missed the real energy source, nuclear fusion.
Right. Once nuclear physics came into play in the mid-20th century, the real picture emerged. Stars spend most of their lives on the main sequence fusing hydrogen. Then they swell up into giants when the core fuel runs out. But the terminology from that old theory stuck around.
Ah, so that's why we still call O, B, A stars early classes and G, K, M stars late classes, even though it's not really an early to late cooling sequence.
Precisely. It's a historical leftover from that incorrect initial model. Kind of confusing, but we're stuck with it.
But one thing that was immediately clear from the HR diagram, and correct, was the link between mass and luminosity for stars on the main sequence.
Oh yes, the mass-luminosity relationship. It's fundamental for these core hydrogen-burning stars. The more massive they are, the brighter they shine. And it's not a linear relationship. Luminosity goes up much faster than mass.
So those really massive O stars, maybe dozens of solar masses,
Are incredibly luminous. B stars, maybe 10 solar masses, still very bright. Our sun, 1 solar mass, G class.
and down to the M dwarfs, maybe only a tenth of a solar mass.
And they are thousands of times fainter. This relationship dictates a star's lifespan. More mass means more fuel, yes, but the hugely increased luminosity means they burn through that fuel ridiculously quickly. O stars live only millions of years. M dwarfs can live for trillions.
Beyond the core physics, spectroscopy tells us about dynamics too, like rotation.
Yep. By looking at how spectral lines are broadened by the Doppler effect, one side of the star spinning towards us, the other away, we can measure rotation speed.
And there are patterns there too.
Definitely. Hotter stars, the O and B types, tend to rotate much faster than cooler stars like our sun, a G star, or the K and M dwarfs.
Why is that important?
The source flags it as crucial for cosmogony, the formation of things like planetary systems. How stars spin down over time seems linked to how they interact with the disks they form from.
Which brings us to magnetism. We can detect magnetic fields on stars using spectroscopy too.
Yes, through a phenomenon called the Zeeman effect, where magnetic fields split spectral lines into multiple components. And some stars have incredibly powerful fields.
How powerful are we talking?
The source mentions fields up to 10,000 Oersted. For comparison, Earth's magnetic field is about half an Oersted, so 20,000 times stronger.
Even sunspots, which are intensely magnetic regions on our sun.
Only reach maybe 3,000 or 4,000 Oersted, so these magnetic stars are really something else.
Now, initially you might think, okay, strong magnets, interesting physics, but what's that got to do with life? But Shklovsky makes a direct connection.
He does. He suggests that these magnetic effects might play a, quote, decisive role in the formation of planetary systems.
How? What's the proposed link?
It likely relates back to rotation and the disk. Young stars often form spinning very rapidly. They need to shed some of that angular momentum for a stable protoplanetary disk to coalesce into planets.
Otherwise, the material might just spiral in or get flung out.
Exactly. A strong magnetic field extending out from the star into the charged particles of the disk can act like a brake. It couples the star's spin to the disk material.
So the star slows down, transfers angular momentum to the disk, and helps stabilize the whole system for planet formation.
That's the leading idea. Magnetic fields act as regulators, helping to create the right conditions in the stellar cradle for planets and potentially life to form. It's a subtle but possibly vital link.
Okay, this feels like the real crux of the matter for the book's theme: universe, life, reason. We're shifting from the star's physics to its chemistry, and specifically, the chemistry needed for life.
This is where it all comes together. When you analyze what stars are actually made of, the overwhelming bulk is incredibly simple.
Hydrogen and helium, like almost entirely.
Almost entirely. Everything else, carbon, oxygen, iron, all the elements that make up planets and people are present only as tiny trace amounts. Shklovsky calls them insignificant contaminations.
Let's look at those average numbers again. For every, say, 10,000 hydrogen atoms,
You get about 1,000 helium atoms, then it drops off a cliff.
only about 5 oxygen atoms, 2 nitrogen, 1 carbon.
And less than half an atom of iron, on average. These heavy elements, everything heavier than helium, make up maybe less than 1% of a star's mass, often much less.
Insignificant by mass, maybe, but their importance is completely out of proportion. The source highlights 2 massive roles for these heavy elements.
Absolutely critical roles. Role number 1, they control stellar evolution itself.
How can tiny amounts of contamination do that?
Through opacity. We touched on this with subdwarfs. Opacity is how much the stellar material resists the flow of energy, the radiation trying to get out from the core.
And heavy elements are much better at blocking radiation than hydrogen or helium.
Much, much better. Even tiny amounts significantly increase the opacity of the stellar plasma. This acts like insulation.
So it traps heat more effectively inside the star.
Right, which changes the star's internal temperature gradient, its pressure balance, how energy gets transported. It fundamentally alters the star's structure, its luminosity, its size, and its entire evolutionary path. A star's metallicity shapes its destiny.
Okay, that's role 1, governing the star itself. But role 2 is the direct link to us.
Role 2. Life simply cannot exist without them. Living matter, as we know it, must be built from complex chemistry involving these heavy elements.
Carbon forms the backbone of all organic molecules. Oxygen and nitrogen are crucial. Phosphorus for energy transfer and ATP, iron and hemoglobin.
Exactly. You cannot build the intricate machinery of life using only hydrogen and helium. It's chemically impossible. You need the complexity and bonding properties of these heavier elements.
Which leads to Shklovsky's unavoidable conclusion.
If there were no heavy elements, there would be no life. It's that stark. It's the absolute prerequisite.
So when we're thinking about where life might arise in the universe, the metallicity of the star and its system isn't just a detail, it's paramount.
It's potentially the first filter you apply. And we do see significant variations in metallicity across the galaxy.
Spectroscopy shows this clearly.
Yes. Generally, younger stars, especially those found in the galactic disk like our sun, tend to be relatively rich in heavy elements compared to older stars.
And the older populations, like the stars in globular clusters or those subdwarfs we talked about.
They are often tens of times poorer in heavy elements. They formed much earlier in the universe's history, from gas clouds that hadn't yet been significantly enriched by previous generations of stars.
So this chemical difference isn't just academic. It reflects galactic history and directly impacts the potential for planet formation and life.
It's fundamental to modern astrophysics. Understanding stellar populations, their evolution, and their potential to host planets hinges on understanding their chemical composition, their metallicity. You need the metals to build rocky planets, and you need them to make the stars behave in ways conducive to life. #tag 8. Out.
Wow. We have really covered a universe of information today, haven't we? Starting with those four basic pillars: mass, luminosity, radius, temperature, and seeing how they lead to things like the density paradox.
Yeah, from the basics to realizing stars come in these wildly different forms, like puffy red giants and incredibly dense white dwarfs.
Then we use spectroscopy, the OBAFGKM sequence, as our key to unlock the HR diagram, that essential map of the stellar kingdom.
And importantly, correcting that map for observational bias to see the real population realizing our galaxy is overwhelmingly run by dim red dwarfs, not sun-like stars.
We touched on evolution, rotation, and the potentially crucial role of magnetism in helping planets form.
And finally, we drilled down into the chemistry. The fact that stars are mostly hydrogen and helium, but that tiny fraction of heavy elements does double duty.
Right. Controlling the star's own evolution through opacity.
And indispensably, providing the actual building blocks for life itself. No heavy elements, no planets, no life, full stop.
It really drives home the connection. Understanding stars isn't separate from understanding life's origins. They are completely intertwined. You need the right kind of star with the right kind of chemistry formed at the right time in cosmic history.
Exactly. Which brings us to that final, really profound question that Shklovsky leaves us with, building on that chemical necessity.
If heavy elements are essential for life, were they always here?
The evidence strongly suggests no. The very early universe, right after the Big Bang, was essentially just hydrogen and helium, with maybe trace amounts of lithium. There were no heavy elements.
So carbon, oxygen, iron,
Yeah.
all the stuff we're made of, had to be created somewhere, sometime after the beginning.
Precisely. They had to be forged inside stars and then scattered through space by stellar explosions, by supernovae. This means the origin of the heavy elements itself is a fundamental piece of the puzzle.
It's not just about stars forming or planets forming or life forming. It's about how the very materials for planets and life came into existence in the first place.
Shklovsky argues it's a problem just as fundamental as the others. So the provocative thought for you listening is this. Consider the atoms in your body. The carbon, the calcium, the iron. Where did they come from?
They were synthesized in the hearts of long-dead, massive stars that exploded billions of years ago.
Exactly. What incredible stellar fireworks, what cosmic recycling had to happen over billions of years just so the chemical ingredients for you could exist here, today. That's the deep connection between the stars and life.